All right, guys, so we've been spending the last few days looking at systems of equations. Specifically, we've been solving them using the graphing method. Today, we're gonna learn a second method. We've got 3 total, called the substitution method, okay? Before we continue though, who can remind me what a system of equations is? Perfect, yep, exactly. So it's 2 or more equations with the same variables, right? So in our system of equations here, both equations are in slope-intercept form, and we decided last week that graphing this is really easy, right? We already know the slope, we know the y-intercept, right? So I can graph this, put in my y-intercept there, graph our slope, and where do we see the solution? Yeah, exactly. So we see the solution where 2 lines intersect, okay? And who can remember why that's the solution? Yeah, exactly, because that's where the 2 equations are the same, right? So these 2 equations are the exact same, they're equal at this point, right? That's where the 2 lines cross, that shows us on our graph that they're equal. For the substitution method, this works really nicely in different scenarios, right? Our first equation here, it doesn't look like it's set up very nicely to graph. Sure, we could solve for y, subtract 2x from both sides, divide by -3. We could find our slope and our y-intercept. However, an easier method here is going to be substitution, okay? And here's the beauty. So the graphing method, we graphed our equations, right? The substitution method, get this, we're gonna substitute, okay? So what that looks like is I have one equation that is in our, what we call standard form, then I have another equation in slope-intercept form, okay? With our second equation, what we really need though is we need our equation to be equal to either x or y, okay? This equation is equal to y, so because it's equal to y, here's what this math sentence says, okay? This math sentence says y equals x minus 1. These 2 are equal, they are the same, okay? These 2 can be substituted for each other anywhere in our system of equations, okay? So if I go like this, would you guys agree with me that these 2 are still the same? Yeah, it's still the same equation, right? It's a different order, it looks different, but it still says y equals x minus 1, okay? So here's how that substitution method works. Because I can trade these, I can substitute them, I can exchange one for the other, I can also substitute in my original equation, okay, my other equation. So we've got y right here, okay? Because y equals x minus 1, I can take y out of my equation, and then I can substitute or plug in, oh, that covered the equal sign, I can plug in x minus 1, okay? So algebraically, here's how this looks. I'm gonna have 2x minus 3. Remember, we've talked about anytime we're plugging something in, we want to include our parentheses. So I plug in x minus 1 where y used to be, and now I have a new equation that is 2x minus 3 times x minus 1. Okay, so again, here's the idea. These 2 things are equal. Okay, they're the same. I can substitute them, flip them, plug them in for each other at any point in time. So what I did was I took my original equations, right? Took out the y is gone, and I put in the thing that equals y. Again, this has to be equal to y. If it's not equal to y, I can't substitute. I can't put stuff in anywhere, okay? It has to be equal to a variable, okay? And now we have a nice equation to solve, okay? So when we're solving this equation, I'm obviously trying to get x alone, right? I only have x's here. And remember when we talked about graphing, I'm trying to find both x and y, okay? So we'll come back to that idea in a second here. I'm first going to distribute this -3. That gives me 2x minus 3x plus 3 equals -1. And who can remember how to simplify this equation? Yeah, combine like terms, exactly. So we can combine like terms. We've got 2x and -3x. Those 2 have the same variable, same exponent. I can combine those. I get -x plus 3 equals -1. Okay, and now I can go ahead and subtract 3 using my inverse operations here. I end up with -x equals -3, right? Exactly, not quite. So I don't have x alone right now, right? We've talked about this. When I have x, when I have a negative sign in front of my x, I divide by, yep, -1. Divide by -1, okay? So we've got x equals +3. Okay, but here's the deal. When we looked at our solution over here, we had both x and y, or we had an ordered pair right here of both x and y, okay? So I have my x, I need my y. In order to find y, I can go back to my equations. Okay, here's the beauty of algebra. With my equations here, I can substitute 3 for either of these x's, and I can use that to find y, okay? But usually with substitution, one of my equations will be easier, okay? For this second equation, it's already solved for y. So rather than plug in 3 for x in my first equation and have to do some inverse operations, do some solving here, this is already solved for y. I plug in 3 where x was, and now I find out that y equals positive 2. And we have our ordered pair. Beautiful. So again, quick recap here. The idea comes in where y equals x minus 1. It must be equal to a variable, okay? If it's equal to a variable, I can substitute in for that variable. In this case, that variable is y. So I took y out of my equation, and I put in x minus 1, right? So that's where this equation came from. I plugged in, or I substituted, x minus 1, then I distributed, I combined like terms, I used my inverse operations right here, found out that x equals positive 3, then I went back to my original equation right here, and I plugged in, or I substituted, 3 for x. Wonderful. All right, and unfortunately today we don't quite have time for our second set of equations. We'll talk more about that tomorrow. You can see it looks a little bit different than the one we did here today. Thanks, guys.